Hey everyone, so in this video we're going to talk about the periodic table of elements. So we've got a whole lot to cover in this video, so let's go ahead and get started. So when it comes to the periodic table, the elements are arranged in order of increasing atomic number, that is the number of protons in the nucleus of each element. The elements are also arranged such that the elements that appear in the same vertical column have similar chemical properties. So this tendency of the chemical properties of the elements to reappear when we arrange them this way so that we can stick them into these vertical columns, this is what we call periodic law. And I have a whole video that explains periodic law in further detail, so if you'd like to, please feel free to view that video. So moving right along, we basically have three main categories of our elements, which are metals, nonmetals, and metalloids. So starting with metals. Metals are on the lower left side of the periodic table, and as you can see, there are more metals than any other type of element. There are more metals than there are nonmetals and metalloids combined. Metals are mostly solids. Metals conduct heat and electricity. They are malleable, which means that they can be hammered out into thin sheets. They are ductile, which means that they can be drawn out into thin wires. They are lustrous, which means that they are shiny. And perhaps the most important property of all is that they tend to lose electrons when they undergo chemical changes. So that's very important, and we're definitely going to see that again later on. So now let's talk about nonmetals. Nonmetals are on the upper right-hand side of the periodic table. They can be solids, liquids, or gases. They are poor conductors of both heat and electricity, and they tend to gain electrons when they undergo chemical changes. So again, metals lose electrons, nonmetals gain electrons. Both of these phenomena are very important, and we're definitely going to revisit that later on. So that takes us right along to metalloids. So these shaded elements are the metalloids, and notice that they are all lying along this bold zigzag line. This is called the stair-step line, and this basically separates the metals from the nonmetals. And the interesting thing about metalloids is that they have characteristics of both metals and nonmetals. Some metalloids are what we call semiconductors, which means they have an intermediate and highly temperature-dependent electrical conductivity. So the interesting thing about semiconductors is that just by changing the temperature of the environment of a semiconductor, you can actually turn a semiconductor into an on or off switch, which makes that highly, highly useful when it comes to things like computers, for instance. So to further classify the elements, we basically have two other classifications that we shove all the elements into, which are the main group elements and the transition elements. Now, in the main group elements, these elements have very predictable chemical properties simply based upon their position in the periodic table. And the columns of main group elements are labeled with a number and the letter A. The chemical properties of transition elements, on the other hand, are much less predictable than those of main group elements, and their columns are labeled with a number and the letter B. So if we look at this A and B numbering system, notice that for the main group elements, it's pretty straightforward. We have 1A, we have 2A, and then over here we have 3A all the way through 8A. But for the transition elements, it's a little funky. We have 1B and 2B over here on the right, and then we have 3B through 7B over here on the left, and then these three columns together all are group 8B. So this is kind of weird, and I don't really like this numbering system very much. But luckily, there is another numbering system out there which simply numbers all of the columns of the periodic table from 1 all the way through 18. So this is the numbering system that I personally prefer, and I use it more often than the other one. So, by the way, a vertical column of the periodic table is known as a group or a family, and a horizontal row of the periodic table is what we call a period. So, this would be group 1, for instance, or family 1, and this would be group 2 or family 2. And then these two elements up here, this would be period 1, and then these 8 elements over here from this one all the way to this one over here, that would be period 2, and so on and so forth. So let's talk about the main group elements in a little bit more detail. So basically we have 8 main groups, and those are the alkali metals, which is group 1A or 1, depending on which numbering system you're using, followed by the alkaline earth metals. Then we have the boron group. Then we have the carbon group, followed by the pnictogens, the chalcogens, the halogens, and then finally the noble gases. So let's talk about each of these groups in a little bit more detail, starting with the alkali metals. So the alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Alkali metals have very low densities, and they're also very soft. Now, I know the word soft doesn't necessarily come to mind when we think of metals, but this is actually a picture of sodium metal right here, and you can cut sodium metal just with a butter knife. It's literally that soft. Alkali metals are very reactive, and if you'd like to see what I mean, just take a piece of sodium metal and drop it into water. Alkali metals have numerous applications. Lithium, for instance, is used to make batteries. This is an example. This is a picture of a lithium-ion cell phone battery. Chances are the battery in your cell phone is a lithium-ion battery. Sodium and potassium are very important, especially in physiology. You have little proteins in your body right now called sodium-potassium pumps that you would be dead without. So in addition to things like cell phone batteries and industrial applications, a lot of these alkali metals are very important biologically as well. So that takes us right along to the alkaline earth metals. The alkaline earth metals are beryllium, magnesium, calcium, strontium, barium, and radium. And the elements that are listed in bold, these are the true alkaline earth metals. Beryllium and magnesium aren't necessarily alkaline earth metals, although this term is often applied to the whole group. So I think for the purposes of general chemistry, you can consider all 6 of these elements to be alkaline earth metals. They have fairly low densities and they are fairly soft. They are also fairly reactive. Magnesium, for instance, is used in biological molecules. This is right here, this is a space-filling model of a chlorophyll A molecule, which is highly important in the process of photosynthesis. And this little yellow atom right here in the middle, this is a magnesium atom. Calcium, which is a trace element that we require in our bodies, is very common. Milk, for instance, is a great source of calcium, and it's also used to make cement, among other things. There's a glass of milk right there. So now let's talk about the boron group. The boron group consists of boron, aluminum, gallium, indium, and thallium. Boron is used to make glasses, among other things. It's also a principal component of sodium borate, also known as borax, which is used as a detergent, used as a water softener, and many other things. You might have seen something like this at your local grocery store. This is a particular brand of borax that, again, you might find that at your grocery store. Aluminum is very important commercially. I mean, we have aluminum cans, we have aluminum foil. I mean, there's aluminum everything. I mean, it's just so important commercially. Okay, so that takes us right along to the carbon group. The carbon group consists of carbon, silicon, germanium, tin, and lead. Carbon is so important that there's an entire branch of chemistry called organic chemistry, which is based on carbon compounds. Carbon is very interesting because carbon can because of the bonding behavior of carbon can bond to itself over and over and over again to form long chains. This is an example right here of a long carbon chain. This molecule is called dodecanoic acid, and carbon, in addition to forming long chains, can also double back on itself to form rings. So this makes the possibilities of how many carbon compounds there are practically endless. I mean, there's just so many that have been identified. Silicon, for instance, is very important when it comes to computer devices and things like that. This is a silicon computer chip. And remember when I was talking about earlier with those semiconductors, silicon is perhaps the most important semiconductor of all, and it has been utilized very, very much in the computer industry. So now let's talk about the pnictogens. The pnictogens consist of nitrogen, phosphorus, arsenic, antimony, and bismuth. Both nitrogen and phosphorus are very important biologically. This molecule right here, this is called glycine, and this is an example of an amino acid, which is an essential nutrient required, for our bodies to survive. And all amino acids contain this nitrogen atom with 2 hydrogens on it. This is called an amino group, and all amino acids have this group, and they are necessary to our survival. So it's very important. Phosphorus is important. This molecule right here is called ATP, and ATP is basically like the energy money, the energy currency that our cells use. And the basically what will happen is this ATP molecule will lose a phosphate group, and that's going to give off a certain amount of energy that the body can use to carry out other biological functions that are energetically uphill. So that brings us right along to the chalcogens, which are oxygen, sulfur, selenium, tellurium, and polonium. Oxygen is the chief component by mass of water, which I can't state the importance enough of water. I mean, water is highly important. It covers about 3/4 of our planet. It makes up over half of our bodies by mass. In case you need a little bit of a refresher, water consists of a oxygen atom and 2 hydrogen atoms together. So again, very important. Sulfuric acid is very important industrially. I think an estimated 85% of all of the naturally occurring sulfur that we can get our hands on is turned into sulfuric acid, which is used very much on the industrial scale. So that's pretty much it for the chalcogens. There's a bottle of sulfuric acid right there. And then we have the halogens. So the halogens are fluorine, chlorine, bromine, iodine, and astatine. And the interesting thing about the halogens is that it's the only group that has all 3 states of matter at standard temperature and pressure, or STP. Fluorine and chlorine are both gases at room temperature. Bromine is a liquid at room temperature, and iodine is actually a solid. So that's pretty interesting stuff. The halogens tend to be very, very reactive. This right here, this is a bottle of hydrofluoric acid, and this stuff is pretty gnarly. I mean, this stuff can actually eat through glass. I mean, it is very powerful. If you ever find yourself in the presence of this stuff, just, turn around and walk in the other direction, because this stuff will really mess you up. So just be careful. All right, so that's the halogens. And the last main group is what we call the noble gases, which consists of helium, neon, argon, krypton, xenon, and radon. And the noble gases are mostly unreactive. They are very inert. They don't really like to gain electrons. They don't like to lose electrons. They don't like to bond with other elements. They're pretty much content the way they are. Helium obviously is used in balloons because it's lighter than air, so it floats when we fill a balloon with it, so it looks nice for parties and things like that. This is a neon sign. Neon glows bright red like this, and neon, among other noble gases, are used to make these cool signs. And I don't know, you may have heard of like argon lasers and things like that. So it's pretty cool stuff that we can do with these noble gases. So that pretty much does it for the main group elements. Now let's talk about the transition metals a little bit. So the transition metals, again, like I said earlier, their properties aren't very predictable, and that makes them have a very interesting chemistry. They form these compounds called coordination compounds, which is basically where you have a central metal surrounded by several molecules called ligands. So this compound here, this is called hexol, and this is an example of a coordination compound. Notice that we have these cobalt atoms in the middle, and they're surrounded by several different ligands. And it's kind of like organic chemistry, where the combinations are very, very vast. You can make so many of these different coordination compounds. There's a lot of applications of transition metals. Just to name a couple, they can be used as coloring agents, chemical sensors. They can be used as therapeutic drugs, among many, many, many other things. This is a ruby and an emerald, and the red color of a ruby and the green color of an emerald are actually, they're both caused by the same atom. It just depends on what kind of ligands are surrounding it. So this is pretty interesting stuff. You can get a lot of different colors caused by what we call electronic transitions in these metals. It's pretty cool stuff. So now let's talk about the inner transition metals. The inner transition metals is this little chunk of the periodic table that is usually on the bottom. And basically, this is just a piece of the periodic table that has been removed to make it more concise. So basically how it works is we have lanthanum over here, element 57, and then it jumps right to hafnium, element 72. And so it's like, where did 58 through 71 go? Well, the answer is they're right down here. 58 through 71, these are what we call the lanthanides. And then the same thing is true for the next period down. We have actinium over here, element 89, and then it jumps right to rutherfordium, element 104, and 90 through 103 are right down here. So this row up here, element 58 through 71, these are called the lanthanides, and 90 through 103, these are called the actinides. So the reason why this chunk of the periodic table has been taken out is because, well, if we included it where it's supposed to go, it would look like this. And this picture is, notice how it's really wide. It doesn't really fit on a sheet of paper very well, and it leaves a lot of white space. So that's why we do it like this instead. It just is more concise, and it's easier to put on paper. So again, intertransition metals is just a chunk of the transition metals that has been taken out and put down there below everything. So now I'd like to switch gears a little bit and talk about ions. Now, what an ion is, it is a charged atom or molecule. And the main group elements tend to form ions that are very predictable in charge. The main group elements like to achieve what's called a noble gas electron configuration. So remember earlier when I said that metals lose electrons and nonmetals gain electrons? Well, a metal will lose just enough electrons to achieve the same number of electrons as the nearest noble gas. Noble gases are very, very stable, and that's why they're very unreactive. And that's why things like metals will lose electrons to be isoelectronic, so to speak, meaning they'll have the same number of electrons as the nearest noble gas. Nonmetals do the same thing, except they'll gain electrons to form the same number of electrons as the nearest noble gas. So again, metals lose electrons. They form what are called cations. A cation is simply a positively charged ion. And to name a metal cation, all you have to do is you just pop in the name of the metal and then add the word ion to it. So for instance, potassium will lose an electron to form a potassium plus ion. This is what we call the potassium ion. So again, potassium, which has 19 electrons, potassium has 19 electrons, it'll lose one of these electrons to have 18 electrons. The potassium ion has 18 electrons, and it has the same number of electrons as the element argon, which is the nearest noble gas. And when it comes to nonmetals, again, nonmetals, like we said earlier, they gain electrons and they form anions, which an anion is a negatively charged ion. So to name an anion, it's a little different from naming a cation. What you do is you take the base name of the nonmetal and you add the suffix IDE, and then you add the word ion. So for instance, oxygen, it'll gain 2 electrons and it'll form the oxide ion. So again, oxygen, which has 8 electrons, because it's number 8 on our periodic table, 8 electrons, it'll gain 2 electrons and it'll get 10 electrons once it has those 2 other electrons. And 10 electrons is the same number of electrons as neon. So again, these main group elements are trying to achieve what's called a noble gas electron configuration. And like I said, for the main group elements, the ions that are formed by the main group elements are very, very predictable. The charges of them are predictable. So on this next slide here, these are all elements that form ions that have predictable charges. Notice that for the alkali metals, they all form +1 cations. They all lose 1 electron to get the same electron configuration as the nearest noble gas. The alkaline earth metals, with the exception of beryllium, they lose 2 electrons and form +2 cations. Aluminum always forms a +3 cation. Nitrogen gains 3 electrons to form a -3 cation. The chalcogens gain 2 electrons to form -2 anions, excuse me. And then the halogens gain 1 electron to form -1 anions. Notice that hydrogen can actually lose or gain an electron. When hydrogen loses an electron, we call that a hydrogen ion, or we call it a proton, because remember, hydrogen has 1 proton and 1 electron. So when you take away that electron, you're left with just a proton. So an H plus and a proton are the same thing. But then hydrogen can also gain an electron to form what's called the hydride anion. So hydrogen's a very interesting element because it can do that. So that's pretty much it for this video. I hoped you took something home from it, and all right, you guys have a good one now.